For centuries, the prevailing paradigm in medicine was this thing called the miasma theory.
Right, the whole bad air concept.
Exactly, the bad air. It was this deeply held institutional belief that diseases were carried by just, invisible clouds of bad air. You didn't have to touch a sick person, and you didn't have to engage in any risky behavior. You merely had to exist in a contaminated environment.
You just breathe the drifting air and you're infected.
Yeah, and I mean, the psychological terror of that theory really came from the ambient nature of the threat, right? The danger wasn't an action you took. The danger was the environment itself. Your normal, required daily functions were the exact mechanism of your infection.
Which is a terrifying thought, because
Yeah.
you can't just stop breathing.
Right. Now, the medical science behind the miasma theory was obviously debunked, but that terrifying core concept, the idea that you can catch a devastating contagion simply by doing what you're supposed to do in an environment you trust, is actually the perfect framing for our topic today.
It really is.
So welcome to a special VolShield Threat Intel briefing on the deep dive. Today, we are speaking to both security leaders and, non-technical professionals alike. We're going to provide a plain language but deeply mechanical analysis of a major tectonic shift in the software supply chain landscape.
And we have a lot of intelligence to cover today.
We really do. Our stack of sources is massive. We're pulling from technical incident reports from Wiz, Akamai, Microsoft Security, Palo Alto Networks Unit 42, and we're bringing in some historical context from Wikipedia as well.
Yeah, and the intelligence across all those reports, it all converges on a single, highly coordinated timeline. We are looking at a fundamentally different class of threat actor behavior here.
Completely. So our mission for this deep dive is to dissect the June 2026 attack on Red Hat's official NPM packages. We're going to examine the mechanics of the breach, but the breach itself is, well, it's actually the secondary story.
The primary story is much bigger.
Right, the primary story, the really chilling reality we need to unpack for you today, is how self-propagating cyber weapons have transitioned from being these exotic tools of lone geniuses to basically free, easily downloadable open source commodities.
And the implications of that shift, they alter the calculus for every single development team operating today. We've moved from a world where attack capability required immense engineering skill to a world where it literally only requires a search bar.
Which is wild. So let's establish the timeline of the outbreak. June 1st, 2026. Researchers at Wiz flag a severe anomaly inside one of the most, rigorously trusted neighborhoods of the software development world. We're talking about the official NPM packages under the @Red Hat Cloud Services namespace.
Right, and for listeners who might be outside the immediate development ecosystem, NPM is the primary public registry where millions of JavaScript projects download their foundational building blocks.
It's the infrastructure.
Exactly, and that specific Red Hat namespace carries the implicit trust of a major enterprise vendor. Yet, Wiz discovered that at least 32 official package releases, which span more than 90 different versions, had been quietly replaced with poisoned copies.
And the exposure radius there is just staggering. Cumulatively, those specific packages average about 80,000 downloads every single week.
Right.
But the critical question is the execution vector, right? Developers weren't clicking on sketchy email links or downloading unverified attachments. They were running standard command line tools.
Right, doing their normal jobs. The mechanism relied on a feature of the package manager called a pre-install hook.
Okay, break that down for us.
Sure. So when a developer types the command npm install to download a necessary dependency for their project, the package manager allows that downloaded code to execute a tiny setup script before the installation even finishes.
Which sounds helpful in theory.
Historically, it was. It was designed for harmless housekeeping, like creating a necessary folder or checking an environment variable.
But in this case, it's just breathing the bad air. You typed a command to do your job, and instantly, without a single prompt or warning, a 4.29 megabyte obfuscated JavaScript file named index.js executes in the background of your machine.
Instant infection.
Yeah. And the fatal flaw here seems to be letting a third-party package run executable code before the user or even the security team has had a chance to inspect it. Can we just turn that functionality off?
You can, actually, and it's a primary defense recommendation across both the Microsoft and Akamai reports. You can configure your environment to use a specific flag, which is npm install -- ignore scripts.
Okay, so that just blocks it.
Right. It forcefully prevents those pre-install hooks from executing automatically. The trade-off, though, is that some legitimate packages genuinely rely on those scripts to compile native code, so turning it off might break your build.
Meaning developers would have to manually trigger the necessary scripts after they inspect them.
Exactly. It adds friction.
Well, that sounds like a necessary friction if the alternative is instantaneous infection. But, okay, let's unpack this because my brain just threw an error trying to process the origin of this code. If Red Hat is this massive enterprise software company with rigorous security pipelines, how on earth did a 4.29 megabyte malicious payload get injected into their official signed packages?
That's the crazy part. The root cause analysis revealed that the attackers didn't actually breach Red Hat's corporate network or their internal servers.
They didn't.
No. They found a single compromised GitHub account belonging to a Red Hat employee. And by borrowing that identity, the attacker pushed what is known in version control systems as an orphan commit.
Okay, let's look at the mechanics of an orphan commit. Because a standard code review process usually involves, someone submitting a pull request, a second engineer reviewing the code, and then merging it into the main branch.
Yeah.
So how does an orphan commit bypass that entire structural safeguard?
Right, so in a Git repository, every single change is assigned a unique cryptographic hash. Normally, changes are attached to branches, but a commit can exist in the repository's database utterly unattached to any visible branch.
Just floating in the ether, essentially.
Exactly, floating there. So the attacker pushed the malicious code as an unattached commit. Then they directly fed that specific commit's unique hash into Red Hat's automated publishing pipeline.
Oh, wow.
Yeah, the pipeline pulled the code via the hash, completely bypassing the main branch and the entire pull request review process.
So the SLSA provenance, the supply chain levels for software artifacts, which is supposed to be the gold standard for security, that ended up validating the malware.
It did.
It's like the SLSA provenance is like a notary stamp, right? The notary doesn't actually read the contract to see if it's fair or if it's malicious.
Yeah.
They just verify that the person signing it has the right ID and that it was signed in their office.
That is a perfect analogy. The Red Hat pipeline worked exactly as intended. It accurately notarized a malicious payload because the instructions came from a trusted, albeit compromised, account.
Which means a valid digital certificate is no longer gospel. The SigStore signing service correctly attested that the package was built by the official Red Hat pipeline. It just proved where the code came from, not the intent of the code.
Precisely.
Okay, so once that notarized poison package is downloaded and the pre-install hook fires, this 4.29 megabyte payload drops. Let's look at the anatomy of this weapon. What is actually happening inside the developer's machine during those first few milliseconds?
The payload is an aggressively multi-layered piece of engineering. First, it unpacks itself using ROT-based obfuscation.
Which is like a classic substitution cipher. Right?
Exactly, and that's followed by AES-128 GCM encryption. So it wraps the malicious logic in these layers of digital armor to blind static security scanners. And then it initiates this brilliant evasion tactic. Instead of executing the primary malware using Node.js, which is the default JavaScript runtime, and exactly where security tools like endpoint detection and response agents are looking.
Right, because that's where you'd expect JavaScript to run.
Exactly. But instead of doing that, it reaches out to the internet. It downloads an entirely different lightweight JavaScript runtime called Bun, and it executes the final payload inside that new environment.
Wait, if it's reaching out to the open internet to download an unauthorized runtime binary, why doesn't the corporate firewall or the network monitor just immediately catch it and kill the process?
Because the network request happens during the NPM install phase. And that process naturally generates massive amounts of outbound network traffic as it resolves dependency trees and downloads dozens of packages.
Oh, I see. So the anomalous request for the Bun binary just hides in the sheer noise of legitimate installation traffic.
Exactly. It's hiding in plain sight. And once Bun is running, it creates an entirely new process tree that most node-focused security monitors are completely blind to.
Wow. Okay, so that covers the evasion. Let's talk about the escalation. The Microsoft security report notes that the malware creates a passwordless sudo rule to give itself root access. But wait, if I'm logged in as a standard developer, a random user-level script can't just make itself an administrator without prompting the screen for my password, right?
Yeah.
How did it bypass that fundamental OS-level security?
It exploits the functional realities of how developers actually work. When a developer types sudo and enters their password for a legitimate task, the Linux or Mac OS environment typically caches that authentication ticket for about 15 minutes to save time.
Right, so you don't have to type your password every 30 seconds.
Exactly. The malware checks for an active, cached sudo ticket. If it finds one, it silently piggybacks on that existing elevated session to rewrite the executors file in the background.
Oh, that's nasty.
Yeah, it grants its own backdoor processes permanent passwordless root access going forward.
So it literally waits for you to open the vault and then it just wedges a doorstop inside.
That's exactly what it does. And once it has that unrestricted access, the memory scraping begins.
And what is it looking for?
The scope of the theft is staggering, honestly. It aggressively hunts for AWS, Azure, and Google Cloud identities. It targets Kubernetes service account tokens, HashiCorp Vault secrets, and CI/CD tokens from platforms like CircleCI. It even targets GitHub Actions.
I want to pause on GitHub Actions for a second, because platforms like that are specifically designed to mask secret values in the logs. They replace passwords with asterisks so they can't be read by anyone looking at the output. So how is a script pulling masked values?
Right, so masking only occurs in the text output of the log file, but the actual running process, the runner memory, still has to hold the plaintext token to authenticate with external services.
Oh, of course. The machine needs to know the password to use it.
Exactly. So the malware uses its newly acquired root privileges to read the raw memory mappings of the runner process directly from the operating system. It bypasses the log masking entirely and pulls the plaintext secrets straight from RAM.
That is deeply unsettling. But stealing credentials is only half the story here, right? Because normally, if we want to contain the blast radius of stolen credentials, the standard incident response is to just immediately revoke those tokens. Once the tokens are dead, the malware loses its access.
You would think so. But the architects of this malware anticipated that exact defensive maneuver. This isn't a traditional Trojan horse that steals your wallet and quietly phones home. It is a self-propagating worm.
And that's a huge distinction.
Huge. It takes the specific NPM published tokens it just stole from the victim's memory, logs into the registry autonomously, and republishes poisoned versions of every other package that specific developer maintains.
So if an open source maintainer with, say, 5 popular utility libraries accidentally installs the Red Hat package, the worm instantly injects itself into their 5 libraries, bumps the version number, and publishes them to the world.
Right. Just waiting for the next wave of developers to run npm install.
The infection chain becomes exponential.
Yes, and to your point earlier about revoking tokens, the payload actually includes a dead man's switch.
Wait, really?
Yeah. It constantly monitors the validity of the stolen tokens. If it detects that the victim has realized they are breached and they revoke the token on the server side, the malware immediately triggers a destructive command, specifically rmsrf, to completely wipe the victim's local home directory.
A scorched earth failsafe. If you lock me out, I burn your machine to the ground.
Precisely. And they left a calling card as well. When the malware autonomously creates repositories on GitHub to serve as dead drops for the exfiltrated cloud secrets, it stamps the repositories with a specific description. It reads, Miasma, the spreading blight.
And that's where the security community got the name for the campaign.
Exactly. They adopted the attacker's own naming convention.
Okay, so the sophistication of the evasion, the recursive worm propagation, the scorched earth failsafe, all of this points to a highly resourced, deeply capable threat actor, which makes the choice of target slightly strange to me.
How so?
Well, why point a weapon this loud and aggressive at an open-source registry just to scrape some cloud tokens, rather than quietly targeting a financial institution or a sovereign state? Unless the attacker who launched Miasma didn't actually write the code themselves.
And here's where it gets really interesting. Tracing the lineage of the code reveals a fascinating origin. Miasma is actually a direct derivative of an earlier worm known as mini Shai-Hulud.
Named after the giant sandworms from the sci-fi novel Dune.
Right, and a threat group named TeamPCP had been operating mini Shai-Hulud throughout the spring of 2026. In early May, they used it to compromise the TanStack ecosystem, and then later that month, they targeted a data visualization ecosystem called AntiV.
And the scale of that AntiV attack was breathtaking, according to the sources. They infected 639 packages in a single hour using the worm's automated publishing logic.
It was industrial-scale supply chain poisoning, so TeamPCP engineers this devastating, highly effective toolchain. But then we hit this critical date in the intelligence reports, May 12, 2026.
Right. What happened on May 12th?
On the evening of May 12, TeamPCP executed a maneuver that fundamentally altered the threat landscape. Historically, top-tier cybercrime syndicates fiercely protect their proprietary malware. But TeamPCP uploaded the fully weaponized, unredacted source code of the mini Shai-Hulud worm to public GitHub repositories.
They open-sourced a weapon of mass digital disruption.
Yes, the credential stealer, the bun evasion tactics, the self-spreading logic, the CI cache poisoning scripts, all of it. Published with a REAFME file free for anyone on the internet to copy.
I mean, the implications of that are terrifying. The Wiz researchers noted an immediate, chilling implication regarding attribution, didn't they?
They did. What's fascinating here is that when Miasma hit Red Hat in June, the security community literally could not attribute the attack to TeamPCP with any certainty. Because the blueprint was public, Miasma could have been deployed by anyone.
Copycat.
Exactly. The researchers observed that the Miasma variant simply swapped out the Dune references for Greek mythology themes, using variables named Spartan instead, and pointed the exact same weapon at a new target.
We really have to contextualize how massive a paradigm shift this is for the security industry. We've operated for decades on a very specific set of assumptions about the barrier to entry for self-propagating malware.
Right. And to understand the modern inversion of that barrier, we need to anchor ourselves to a specific historical event. Let's go back to November 2, 1988. A Cornell graduate student named Robert Tappan Morris released what the world now recognizes as the first major internet worm.
The Morris worm. According to the historical context in our sources, it ended up infecting roughly 6,000 machines, which was an estimated 10% of the entire internet at the time. It partitioned networks for days and led to the first felony conviction under the U.S. Computer Fraud and Abuse Act.
Right. The Morris worm was a catastrophe. But it was a catastrophe that required rare, exceptional genius. Robert Tappan Morris had to deeply understand the VX and Sun 3 system architectures. He had to handcraft exploits for specific buffer overflows in utilities like Fingered and SendMail.
It wasn't something you could just copy and paste.
Exactly. Self-replicating code that could navigate disparate operating systems without crashing was an exotic, highly difficult engineering feat. The number of humans capable of writing a functional worm back then was incredibly small.
The barrier to entry was a massive high wall. But Miasma relies on the intended design features of the modern ecosystem. It doesn't need to exploit a buffer overflow. It uses the pre-install hook exactly as the package manager designed it. It doesn't need to crack a password. It uses the automated CI/CD pipeline exactly as the enterprise architect configured it.
Right. The vulnerability isn't a bug. The vulnerability is the workflow itself.
And that means the high barrier to entry has entirely collapsed. We are no longer living in a world where attack capability is defined by rare engineering skill. Attack capability is now a free, easily copyable commodity. You don't need to be Robert Tappan Morris anymore. You only need the ability to read documentation and click download.
It's a complete inversion of the old model.
But hold on, let's talk defense. If we strictly lock every dependency and refuse automatic patches to stop malicious updates from sliding in, aren't we just trading one massive risk for another? I mean, if we pin everything to an exact version, we block the Miasma worm, but we also block critical security updates, leaving ourselves vulnerable to known 0 days that the maintainers are trying to patch.
And that is the ultimate tightrope walk of modern software development. The Palo Alto and Akamai reports stress that dependency locking must be paired with active vulnerability scanning. You pin your dependencies with exact version numbers and cryptographic integrity hashes, so a package manager cannot pull down a poison version pretending to be an update.
Okay, so you lock it down, but then how do you update?
When a security patch is released, you manually verify the new hash, audit the changes, and intentionally update the pin. You move from implicit trust to explicit verification.
Got it. And regarding the evasion tactics, if the malware is spinning up completely new process trees with that bun runtime, how do security teams catch the execution if their EDR tools are blind to it?
You have to shift your detection from the process level to the network level. The absolute signature of this attack is a package making anomalous outbound network calls during the installation phase, either to download payloads or to phone home.
So watch the network traffic during the build.
Exactly. Security teams must monitor their CI pipelines for unexpected outbound traffic during the build process. If an npm install command suddenly tries to open a connection to an unknown IP address, the pipeline should immediately terminate.
Verify, but be skeptical, even of valid certificates. Let us synthesize the scope of this intelligence. The June 2026 breach of the Red Hat NPM packages was a masterclass in exploiting trusted automated systems. It bypassed human review using orphan commits, it forged SLSA provenance by abusing the legitimate pipeline, it evaded node-focused security by downloading the bun runtime, and it achieved passwordless root access to scrape heavily guarded cloud credentials.
The technical execution was virtually flawless. But the true, lasting lesson of Miasma is the commoditization of the capability. When TeamPCP open-sourced the mini Shai-Hulud worm, they effectively democratized supply chain poisoning.
The threat matrix has fundamentally shifted. The danger is no longer isolated to the genius who spent 6 months writing the contagion. The danger is that the genius's work can be deployed by anyone with an internet connection. You publish the recipe for a weapon, and you don't just get one outbreak. You get an outbreak every single time someone decides to copy the repository.
It's no longer a question of who has the skill to build the weapon. It's simply a question of who decides to download it today.
Exactly.
And, that reality forces a very uncomfortable question about the immediate future.
What do you mean?
Well, the sources outline the crisis of human copycats downloading open-source malware. But we are rapidly approaching an era where autonomous AI coding agents are routinely deployed to optimize codebases and manage environments.
Oh, wow. I see where you're going with this.
Right. If a self-spreading, highly evasive cyber weapon is simply sitting in a public GitHub repository, it requires no imagination to see an AI autonomously discovering it. An agent could download the blueprint, dynamically modify the obfuscation to evade the newest signatures, and deploy variations of these commodity weapons at machine speed.
So if the only barrier to entry is clicking download, an AI can execute that action a million times a second.
Creating an automated, continuously evolving miasma that we cannot even see coming until the environment is already saturated.
An automated miasma. The bad air just keeps writing itself. It brings the analogy full circle, doesn't it? You do not have to do anything wrong to catch it. You simply have to install the things you need to survive. Thank you for joining us for this VolShield Threat Intel briefing on the Deep Dive. Stay curious, stay pinned, and stay safe.